Now, one thing you might notice here is that this first exposure to HCl has a much bigger response. It doesn't recover as much, and then it comes back to basically the same level. And we saw this phenomenon in all the sensors. We're not exactly sure why it happens, but for some reason, when these sensors are first exposed to the gas, they experience a very great response. And no matter how long it takes to recover, the second, third, and fourth responses are much more stable, but much lower. So in order to get a more accurate depiction of the data, we only compare the second exposure. And as you can see, once again, the pyridinol and the ODA perform much better than the ALF and P2. So now we'll take a closer look at the ODA and pyridinol and see what's really going on. So here's the ODA, and you can see it does get a pretty good response. But there's two things that make it less viable candidate for a good basic or acidic sensor. One, if you look at the points where the resistance recovers, you can see that over time it does not recover full resistance, which means that when you're detecting a change in response, you're going to get varied results. Another big problem with the ODA was its conductivity. Like I said, it was the biggest sensor, which means it should have been the most responsive and had least resistance. But as we found out, at 1 volt, ODA, the graphs were extremely noisy and frankly inaccurate. As you can see, there's no real change between these concentrations. When we increase the voltage to 20 volts, we got a cleaner, more accurate graph, but this also means that we need a higher power consumption for the ODA sensor. In the lab, this is okay, but in real-world applications, we don't always have 20 volts to back up. Now, if we look at the pyridinol graph, you can see it looks a lot different. And there's a few things that make it stand out from the other sensors. First of all, the recovery seems to be pretty consistent. Each time after it's exposed to the gas, it seems to recover most of its resistance. The second thing you might notice is that the graph's a little choppy because you have these plateaus at the bottom of the curve. Now, this indicates that there's a lack of change in response at that time, which means that it's actually responding to the gas even quicker. And this makes it much more advantageous than the other three sensors tested. Now, the real mechanism behind pyridinol being so good is its base association constant. Obviously, this indicates the strength of a base, meaning a lower ppb value, a more basic compound. And as you can see, of the three functional groups, pyridinol is the lowest, but isn't a strong base. We still want to use weakly basic compounds to avoid too much interaction, but pyridinol stands pretty low on the scale of bases, but a much stronger base than the other two functional groups, which is the main reason why it outperformed other sensors. Now, another thing that we tried during the 10 weeks I was here was annealing. And in the past, this had indicated improved sensitivity because mainly what it does is it gets rid of impurities. It's heat treatment in a vacuum, heated for about 150 degrees for an hour, and the goal is to remove excess salt and act as an impurity. However, when we actually tested these with our sensors, we saw the only difference between this is there's greater response for the first sensor, but after that, the response is pretty much decreased overall. And it really didn't improve the sensitivity of any of the sensors. So obviously in 10 weeks, you get some done, but not everything you want. And some further work that can be done in this research is consecutive tests. We tried this a couple times experimentally in the lab. We got some interesting results, but basically consecutive tests means taking the sensor and putting it in a real-world scenario where it's exposed to different concentrations of gas very quickly and seeing how the response changes. Another thing that can be done is in situ analysis, which is where you expose these sensors to a gas with the presence of near-IR spectroscopy and really look at the mechanism behind what's happening in the chemistry. We tried to do this in the lab while I was here, but we didn't get the results we wanted, so you can always make this future work. Like I said earlier, we could also test this at a lower voltage. We picked 20 volts just to get clear experimental data, but in real-world applications, you might want something lower than 10 or even down to a battery like 5 volts. There's also the question of thickness versus sensitivity. We know that thicker film is more conductive just because it's more energy to bridge those electron gaps, but that doesn't really indicate a change in sensitivity. So we may see differences if we compare these two. And with that, I'd like to thank you all for being here. I'd especially like to thank June and the entire Sunrise program, as well as the Center for Nanoscale and Science Engineering, my professor, Dr. Robert Haddon, and the entire Haddon Research Group. Thank you. questions? Yeah, go ahead. I actually got it in India. It was handmade. It's also much cheaper. So next time you're in India, all of you, come see.